Summertime is coming, so today we're going to talk about some highly non-trivial theorem. It's called Stokes theorems. So as you can see from the figure here, that this is a stock and the statue is under the float, is surrounded by the float. So Stokes not only provide a very beautiful proof for the Stokes theorem that we are going to talk about today. Stokes is a great scientist which also who has made major contributions to basically the Navier-Stokes equations playing very important role in hydrodynamics. Okay, so today we're going to talk about one of his famous result. That is a Stokes theorem. That is, suppose now you take a contour and also a surface of it. For an open surface like S1, then it has this it's basically ended with the boundary, that is the closed contour, and the closed contour is denoted as ds. And just as the Gauss theorem, here again we have what we call the bulk boundary correspondence. That is the vector field, the circulation of a vector field through the contour, that's a partial S, equals the curl of the vector field through the surface. That's pretty amazing. And after explaining how this works in simple cases, we will call out not Mr. Q but Miss Loop. And after providing a fundamental proof in 2 dimensions and generalize it to 3 dimensions, we will also then mention whether these Stokes theorems works or not for another very interesting thing called Mobius strip. And I do hope that you will enjoy the videos today. And so let's begin. Well, in fact, before we begin, let me state this in Mandarin. 那大家知道，其实再过这个是我们在 Vector Calculus 的最后一堂课。那接着再下来之后，我们就要进行到 ODE Ordinary Differential Equation。那很快的，其实我们就要期末考了。那我知道在疫情的时候，大家可能不是很容易专心，但是请大家务必要多多看课本，然后看不懂的话可以来看一下我们上课其实是上讲解的内容。那如果还是不懂的话，可以去上线上的习题课，或者是直接在e-learn上面留言，然后把你的问题提出来。那我们如果看到的话，都会尽快的提供大家解答。那还是再一次提醒大家，呼吁一下。我知道在疫情的时候，就我旁边收集到的资讯，大家似乎都已经停止学习了。那这个到期末的话，会是蛮严重的，因为我在期中考批阅各位的考卷的时候，发现大家其实目前对于整个应用数学的理解状况，并不是到很理想。OK， so keep up the good work. So then let's go back to the learning material today that I will walk you through with the Stokes theorems. First of all, let's recall the definition of a curl. So a curl can be viewed as the outer product of a vector field with the del operator, and in Cartesian coordinate, you can write it down this way. And after calculating the determinant, you will get the x, y, and z component of the curl. And the job today we're going to show is that the vector field and its corresponding curl is still a vector field, satisfy this bulk boundary correspondence. So how are you going to proceed? Well, before we dig into the technical detail that how you can actually calculate the surface integral and relate it to the boundary integral, the contour integral, which we call circulation, I would like to emphasize the non-trivial part of Stokes theorems. Think about this. Just think about this. Suppose now you have a surface S1, as I plotted in green here. Its boundary is a circle, as I highlighted as red, and its directional is determined by the right-hand rule. Okay, but so the Stokes theorem basically said that if I calculate the curve through the surface, it would be related to the circulations on the boundaries. But this is not really the same. You might think that Stokes theorem is just another version of Gauss theorem, but it's not. Think about that. In 3 dimensions for a closed surface, the volume inside is uniquely defined. On the other hand, in 3 dimensions, given a contour, the open surface is not uniquely defined. For instance, here is another example. I just choose a very simple flat circle areas, S2s, which also share the same boundaries. So the non-trivial part about Stokes theorem is not just relating the surface integral to a corresponding contour integral. As long as different surfaces share the same boundaries, the result will be the same. And this is highly non-trivial. And the reason why it is with this complication is really coming from that the surface itself is a vector. So it's not as simple as the volumes as in Gauss theorems. And the second thing is that the Stokes theorem doesn't really work for one-sided surface. So typically for open surface, there would be like one direction and the opposite direction. For closed surface, this is even more trivial. There you have interiors and exteriors, so that you can differentiate. So a surface then have two sides, which means if you wander around on one side, you will never go to the other side without crossing the boundaries. But they are one-sided surface like Mobius strip, which we will explain a little bit. And then when you try to apply Stokes theorems, you'd better be very, very careful. Okay, so these are the two general conclusions that I would like to make before we dive into the technical detail. And so here we comes. That's just call out Miss loop, okay, on the xy plane to prove the theorems. So on the xy plane, this Miss loop take a relatively simple shape. That's dx, dy, dx, dy. Okay, so let's calculate the circulation first. That is the contour integral of this. So it contains 4 segments, and we will calculate their values in 2 pairs. So the first one is that's just calculate the dx contribution. So this dx contribution contains 2 parts. The first part is this. So that's vx dx. And the second part is in opposite direction, remember? So there's a minus sign and also vx dx. The tricky part is that when computing these, the component, the vx component here occur at y, where the vx component here occur at y plus dy. Okay, and so combining them together, you got this term here. On the other hand, if you try to do the dy, then you realize that here, this is a positive contribution. Here is flowing down, so that's negative contribution. Here it occurs at x. Here it occurs at x plus dx. So sorting everything out, we need vy component at x plus dx minus vy component at x. So that's it. So the circulation can be written this way. And by now, you should be familiar with all the tricks that we are going to use. That's just the partial derivative of the vector field. So this can be expressed as a partial derivative with respect to y, because other are held constant and only y is changing. And so this will amount to, remember that this is y plus dy, so this corresponding to minus dvx dy. On the other hand, this is vy, but then the variables x is changing, so this equals to the partial derivative of vy with respect to x. So this is dvy dx minus dvx dy. And one can, of course, here you get a dx multiplied by dy, you get dx dy. Here you get a dy dx multiplied together, you got dx dy again. So you already see the circulation here, the circulation of the boundary turn into a surface integral. Okay, so writing this term and then recognizing that this is nothing but curl v that we calculated, dot k in the z direction. So then we sort of understand that this, if we just try to write these answers in vector form, okay, then this is curl v dot k dx dy, and curl v dot k is just the z component of the curl. So then you got this the same result here. So at least for a mixed loop on the xy plane, this is correct. But of course, you can think about that with just performing the coordinate transformations. There's no reason the xy plane is so special. So then for any directional loop, the result remains the same. In particular, we have written it in vector form, and so thus this would always be the same. And the second thing is this very cute part. Suppose now you take two mixed loops together and then getting close. So you know that this cancel out. So the sum of circulation is exactly the same as the larger circulations around this whole area. So that means that you can actually combine many different mixed loops together, and eventually will get into an arbitrary contour on the xy plane. Okay, here comes a highly non-trivial part. The proof that I provided here will certainly works for any surface which is flat, or the contours which can be placed on a flat surface. And of course, the Stokes theorem works in 3 dimensions. And so the proof then becomes rather technical and complicated, which I won't explain in the applied mathematics course. If you are interested, you can go to Wikipedia, then you will find that the proof can be separated into 4 logical steps, and step by step, then you can get the ultimate forms of the Stokes theorem. Okay, so I was skipped out, and I just emphasize one more time that when you write that the circulation around the boundary equal to the corresponding curl, the surface integral of the corresponding curl field, this is highly non-trivial. We only, the proof that I provide here is really the flattened version of the Stokes theorem. I only provide the proof on the surface, but then these results can be really generalized to 3-dimensional cases. And for those mathematical geeks that you are interested in the technical proof of the Stokes theorem, you can find a pretty amiable versions in Wikipedia. So have some fun there. And so this the following 5 minutes is going to be a recap on the conservative field. And so if you attended the lectures of Green theorems, and also his novel idea about potential theories, all the material that I'm going to talk should sound rather familiar. So I'm going to go through this whole thing relatively quickly, so then we will land on the important examples for the Stokes theorem today. So suppose now I consider a vector field as irrotational. So irrotational just means that microscopically you calculate all the curves, it is zero everywhere. And since it's zero everywhere, of course, if you just calculate the surface integral of the curve field, no matter what kind of surface you choose, it's still zero. Then according to Stokes theorem, that just means that when V is integrating over arbitrary contour, closed contour, the circulation is zero. This zero circulation is a very interesting properties of irrotational field. Okay? And once you know that, because the circulation of any closed contour is zero, we can just consider two line integrals. For instance, like the gamma 1 and the gamma 2 connecting the same endpoints. Defining I1 as V dr along gamma 1. Define I2 as the line integrals V dr along gamma 2. Okay? And because gamma 1 and gamma 2 are not the same, so this is gamma 1, this is gamma 2, and because they are not the same, so the result might not be the same. But however, here we observe a very interesting thing. That is, if I now just reverse the direction of gamma 2, then this whole thing will make a closed contour. And since I'm dealing with a rotational vector field, the circulation is always zero. So what does that mean? That means that the line integral along gamma 1 and gamma 2 would always be the same. So writing it down, that means that along gamma 1, along gamma 2 are always the same. So the dependence then fall on not on the path, but can only depend on the endpoint. And thus, that means that there exists a potential that we can define so that these line integrals doesn't matter what paths you chose. It would only, its value is fully dictated by the endpoints, and thus phi RB minus phi RA. So that's something amazing. Okay? And also a small remark that try to write down the Maxwell equation and you will find Faraday's law. And so Faraday's law in modern form is written this way. That means the curl E is minus dB dt. So if you have a static solution, that is that the B field doesn't change with time, so then you got curl E equal to 0. That means that electric field is irrotational. Thus, this electric field can be written as minus gradient phi, and this phi is electric potential. So that's what you typically learn in general physics. However, there is no reason why dB dt is always 0. In general case, in particular in the presence of electromagnetic field. And so what is electromagnetic field? The reason why you can see me, it's just because this dB dt is not 0, right? I'm shining, there have been photons shining on my faces, and you are using mobile devices or computer to watch this video. So of course the dB dt in real life typically is not 0. This is more of a special case. And the general case is that this E cannot be solely described as just a gradient of some potential. And thus, please do not confuse with the two important facts. The existence of electric potential relies on whether the electric field is irrotational or not. On the other hand, no matter whether you have dB dt setting to 0 or time varying, there's always electric energy, right? Or electromagnetic energies. So apparently we don't really rely on the presence of electric potential to compute the potential energy stored in electric and magnetic fields. So please do not entangle these two things incorrectly. They're separated concepts. Okay, so that's a side remark when applying Stokes theorem to Maxwell equation. Okay, this is really awkward, so please excuse me. Somehow the phone is ringing. Be back in 30 seconds. This is what happens when you have just one person sitting in a studio and then try to air out YouTube. Sorry about the disturbance. Let me see how many audience I have lost due to this incident. Oh, okay. Great. Seems to be okay. Yeah. Doesn't seem to losing. Yeah, he does not seem to lose too much. Okay. Okay. So let's come back to our learning material. In fact, today, in order to show some of the mathematical programs, I have set up 3 different studios to share with you. So here, let's just try to calculate the circulation of a field. Okay, suppose now I have this very interesting example here, that this is a semi-sphere. This is a semi-sphere. So you have a sphere which is x squared plus y squared plus z squared equal to a squared on the positive side. And so let's say that I was given a field like this, V, and it's 4y, x, and 2z. So it's a vector field. And we're curious. Curious about what? We're curious that I want you to take the curve first. Okay, calculation. Step 1. And through the area. Okay, through the area. Sticky. This doesn't sound very easy to compute, right? So you need to change V into another vector field, curve V, and thus you need to perform this highly non-trivial surface integral over the semi-sphere. And so there are 3 ways to go. The first way is the hardest way and the most straightforward way. That is, why don't we just directly calculate the surface integrals? Okay, so then the first step is that writing down the curve of the vector field. So ijk dx dy dz, ordinary stuff, 4y xz. Okay, so I calculated for that. If you calculate this, that's 0. If you calculate this, it's still 0. If you calculate that, okay, non-trivial, it's a -3. So we got a curve which is basically just a constant field along the z direction. That means that this field has a tendency to rotate clockwise. Okay, so that's the first step. Second step, this is tricky because we want to integrate over the surface, right? So I'm writing it down here, and let's look at this surface element here. These surface elements contain 2 sides. The top view, if you look down from here, first of all, you see that if you look, let's look at the side first. If you look at on the side, you see an arc here. This arc here, this is the radius r, and then this is d theta. So the length here is r d theta. Okay? And also, you need to know another length here. And you just look from the top. If you look from the top, right? So then this will be something like this. I'm plotting it this way here. then you got a d phi, but then the radius is only r sine theta. So then this is r sine theta d phi. Okay, so this is r d theta and this is r sine theta d phi. And thus you know the areas of this infinitesimal area. And so this dA here is the normal direction n, and then these two multiply together. So then you can use the parameters theta and phi to express the dA vector surface element. So this is r squared sine theta, d theta d phi, and the n hat. And so then let's try to calculate what happens. So curl V dA can be written down. First of all, is a hemisphere. So then this d phi angle still going through 0 to 2 pi. But this d theta angle only go from 0 to pi over 2. So be careful about the upper and lower limit here. And curl V is just minus 3k hat as we calculated before, and dot is a radial direction n. But k dot n, the radial direction dot k, it's just cosine theta. Okay, so writing everything down, you got a double integral with the integram equals to minus 3a squared sine theta cosine theta, and integrate over these with the proper upper and lower limits. So the integration is trivial because there's no phi dependence. You can carry out the d phi with 2 pi. That should be easy. Putting out the constant, this is sine theta cosine theta. You just put it in and then do the integral. So at the end of the day, you got minus 3 pi a squared. So that's it. So that's the hard ways. And try to really understand the logic flows. The logic flow is the following. I give you a vector field and ask you to compute the surface integral over the curve. So the logic is that you need to figure out the vector field curve first. So compute the curve. And you also need to understand the surface elements better. So then you write down the dA element. Then you perform the inner product of these two vectors. You should come up with a double integral and you perform the integration to get the final result. So that's it. So that's really, really straightforward. But suppose now that you understand Stokes theorem, you then realize this is not that hard, right? This whole surface integral can be converted into a contour integral on the xy plane. And everything is relatively simple because the v is already given in the problem, it's like this. And the dr, if you just write down on the xy plane, this is a d phi and dr is this direction. So that's not hard. That dr is just its magnitude is dr and in the e phi direction. And the e phi is minus y divided by a, x divided by a. So you multiply them together. This will just give you this. And so performing the inner product, then you get this is 0. And so this is x squared. This is minus y squared. And so writing it down and re-express in terms of theta and phi. So right now, because you are doing the contour integral on the xy plane, hopefully you should get something which depends on phi, but not theta. So please do not confuse. The theta here is already fixed at pi over 2. That's why that this will be easier than computing the surface integral because there's only one parameter. And so this is y squared. If you square it, then that's sine squared, and x squared, that's cosine squared. And combine them together. okay, using cosine squared plus sine squared equal to 1, you can eventually turn this into 1 minus phi sine squared phi a squared d phi. So then, just perform the integral. So this, making, first of all, this is the surface integral we're interested in, turn it into circulation, and the circulation can be written as the integral over d phi. And this d phi is a circle, so this is 0 to 2 pi. So then this is a squared, 1 minus phi sine squared phi. And the integration again is trivial. That is 1 just give you 2 pi here. And this sine squared, you can, again, fundamental, you just calculate that, they give you 1/2, and so then this is minus phi half. And carry out the algebra, again, you got minus 3 pi a squared. So this is a very good example that you in fact calculate the circulation, calculate the surface integral of the curl, and verify the Stokes theorem indeed works rather well. And finally, we have the third method, which is really cute. And you need to think a little bit more. So according to the Stokes theorem, it's a Stokes theorem then that you can convert the surface integral of the hemispheres as the circular contour integrals, right? So the result should be the same. And you found that computing the circulation is easier. But there are even, well, there's something, if you really understand Stokes theorems, you can actually make it even simpler. That is, I would just choose a different surface. That is the disk on the xy plane, right? So that's legitimate because Stokes theorem didn't really enforce you to choose which surface integral to calculate. So then the surface integral over the hemisphere should be the same as the surface integrals over the disk, right? But this is almost trivial. So what we have done is that we're using the fact that because these two surface integrals share the same boundary, the circular integral, so then their surface integral should be the same. And how can you calculate this? Well, simple. The area here is always in the z directions, and the curve here is also in z directions. And so you multiply them together and it just gives you minus 3. And the area integrate to the pi a squared. So it's minus 3 pi a squared. Wow, it's as simple as that. So this is remarkable. And so I hope that this example provides you the 3 different ways to calculate the surface integral over the curves. And please go through this example and making sure that you are familiar with all 3 different methods. So a quick recap. When asked to compute the surface integral of the curves, method number 1, most straightforward way. Most of the time, the most straightforward way would be technically more challenging, right? Because there are no free lunch in the whole world. So the first one is just compute this directly. The second idea, instead of calculating the surface integral over the hemisphere, one can try to calculate the circulation over the circle. Okay, so that's method number 2. Method number 3 is try to calculate the surface integral over the disk, and it will. All 3 different methods give you exactly the same result. Amazing, isn't it? Okay, so that says this is applied mathematics. So let's try to apply this whole ideas and then go back to the magnetic fields, because the magnetic field looks like it's going to be rotating, right? That's actually quite an illusion. So I'm going to introduce a very interesting idea. It's called vortex in the field. And so the direct consequence is that the current, the wire of carrying some non-zero current turns out to be the vortex in the magnetic fields. And for most of you living in Taiwan, the idea of vortex should be relatively simple. That every summer we would have quite some typhoons visiting Taiwan, right? So typhoon is just some forms of vortex in the air first. Okay, so let's just look at this example. Relatively simple. A long straight wire carrying non-zero current I, it will produce a circulating B field around that. And if you write it down, it's mu 0 I divided by 2 pi rho. Rho is the distance to the wire. And then the E phi directions, which can be written down as minus y divided by rho, x divided by rho. And it's straightforward. That you can actually calculate the curves of this whole thing. And we have done that. And I leave you to think that why this whole thing lead to some really interesting results in previous video. If you forget, you can go back. And if you calculate curve B, the correct answer you should get is that it is 0 except at the origin. So now you know, even though that this field seems like rotating, that's an illusion. It only looks like if the reference point you choose is the origin, then this field looks like rotating. But then if you are choosing a different reference point, in fact, you don't really find the field is rotation around other reference points. So this curve B is directly related to where that location carries non-zero current or not. And because this is just a thin wire thread through this space, so then only the origin will carry non-zero current. So please keep that in mind. But because any other different locations, the curve B is 0. So that doesn't stop us to just introduce a very interesting, what we call the magnetic potential. So I write down the answer for you. That suppose now I just write down the potential for the magnetic field, which is mu 0 I, and then the angle phi. Or you can write it as arctangent y divided by x. And it's a straightforward exercise here. So here, in order to not to, here because the magnetic potential is not that well often seen, so I'm skipping the minus sign here. Sorry, I'm following the mathematician's convention. So if you take the gradients, which is dvb dx, dvb dy, and dvb dz, and you can directly calculate this whole thing because this vb here does not depend on z, so it does not generate any z components. And taking the arctangents just give you 1 over 1 plus x squared, 1 over 1 plus y over x squared, and then taking the partial derivative with respect to x and y, then this is what you got. And sorting out the algebra a little bit, then this is the final result you will get. So verify the algebra and convince yourself, in fact, with this potential, you can generate the correct form of the magnetic field. Okay, so stop saying that the magnetic fields do not have potential anymore. It's slightly deeper than that. Okay, it's slightly deeper than that. And of course, you may come back to the old puzzles. That is because the B field can be expressed as the curl, the B field can be expressed as the curl. And if you really, the gradients, I'm sorry. And if you have some gradients and you are calculating this whole thing because it only depends on the difference between the endpoint, but the endpoint is the same because you complete the circle, and so that should be 0. Well, that doesn't quite work here. Why? First of all, on physics ground, we know Ampere's law. So then the circulation here equal to mu 0 I, so it shouldn't be 0. And in cylindrical coordinate, we can rewrite this whole thing, as I said, is proportional to the phi angles. So then this brings up a very interesting idea, is what we call the winding number. Basically, for a wire thread through like that, that really depends on how you choose your contour. If your contour is something like that, didn't really enclose this, so then it doesn't, when you try to go through this wire, its winding number is 0. That is the angle changes and then change back. On the other hand, if this contour encloses the origin once, so if you go through this whole things, you will find that this angle that you got is 2 pi. And in fact, if you choose a more complicated contour like this one, you will find that you will just wind through the origin twice, and thus give rise to 4 pi. So this is actually something really cute. That is, mathematically speaking, when you have a thin straight wire through this space, it created the B field. This B field contains a very interesting property. That is, you can treating this as a vortex. And so when you do the circulation, if it doesn't enclose this vortex, it will go to 0. And this 0 actually ensures that's why that when you try to compute curl B's, it's always going to be 0, because when you are trying to do some of the points, and you can always find the neighborhood and calculate the circulation, it should be 0. On the other hand, if you enclose the vortex once, then you get 2 pi, and if you just circle it twice, then you get 4 pi, and that is the highly non-trivial winding number. And you can see the presence of the vortex now present a very simple yet charming characterizations for the topological properties of the loops. And this turns out to be true. So the correct form of the circulation should be written as mu 0 I, the presence of the vortex, and the winding number. And because the winding number changed from 0, 2 pi, and 4 pi, so there is no confusion at all. That really depends on how you choose your contour. So it can be 0, it can be mu 0 I, typically taught in textbook, but it can also be what? Be 2 mu I. And is this really surprising? It's actually not. Think about that. Previously, we try to cheat the high school students that when you're passing through something, right, in the solenoid, and there's a mysterious way that you need to multiply n times. Why is that? Think about that. This is the solenoid rounding 2 times. You can round it n times, and then you get a factor of n in front. And that's why with the same current, if you just wind it up many times, then you get different answer out. That's actually the same mathematical structures. Try to keep that in mind. Okay? So that's basically all the material that I try to cover today, and let's try to have some fun. Oh, here is the side remark again. So if we really try to compute the curves carefully, you will find that the curve B is 0 everywhere except at the origin. And in fact, at the origin, again, there is a delta function appeared there. And this is what I introduced as the vortex. So this is mu 0 I, the strength of the vortex, and this vortex happens on the plane is delta x and delta y. And because you have a delta function here, that's why that when you try to do this, okay, and if you just integrate over that, and if you just choose circling it once, then you cancel this with the surface area, and then you get mu 0I. That's how we really get the Ampere's law. So the integral form and the differential form match up with each other. There's no discrepancies in between. Okay. So let's go back to the Stokes theorems. So their rumors or their discussion debate whether Stokes theorems works or not for one-sided surface. So here I use Mathematica to plot the one-sided surface. This is the Mobius strip, which you can make by really just attach a piece of paper together. And so you can see here, let me just suppose you start from here. This is really a closed contour, right? You go through here, passing through there, and then go through here. And to make it visually clear, I actually move the contour here, so then you can see it just went through twice. And you might aha yourself that this contour doesn't look that unfamiliar, because this contour seems very close. If you project it on the XY plane, it is like something like this. Okay? And yes, your observation is correct. So can Stokes theorem apply to the Mobius strip or not? Well, you can think about that. And so let me switch to how you generate this Mobius strip mathematically. So then you sort of understand and you can play around to check whether this is correct or not. Okay, so first of all, let me do a little switch to call out my computer programs. And meanwhile, okay. I also got a question. Is the winding here the same as the one in string theory? Yes, yeah, that's the same winding number. Good questions. Great. So I got a camera here, I got the desktop, so we are going to switch to the third thing. So hopefully everyone has seen a program like this. And I do encourage you to really just write your own program to generate the Mobius strips. So the Mobius strip as a two-dimensional surface, of course, can be generated with two parameters, u and v, right? Let me get some tea here. So if you write x, y, z with u and v, and you find that x and y is 1 plus half v over 2 cosine u over 2, and the sine u over 2 is over here, and later this is cosine u and this is sine u. And if you now then just change, for instance, v from -1 to 1, and u from 0 to pi, and plot it out, you will get a Mobius strip. Let me run it for you. You will get a Mobius strip like that. And so you can rotate it to see that at different view on the side, you can see why you can make this from a strip of paper and rotating them. Okay? And this is really cute because if you just do this, that's the other side of this whole things. And if you then, since you are making this paper, this Mobius strip, by cutting a paper sheet and then rotating it and then matting it together, imagine that you are an ant. If you just follow this on the surface, you will basically run to the other side and then going back. And that's why it's called one-sided surface. That is, there is just one side. There's no two sides. And then you run into big troubles. if you go back to the Stokes theorems, you know, okay, if you really go back to the Stokes theorem, you know that if you choose one direction, you should get answer, and if you choose the other, you get the totally opposite side. So with the Mobius strips, you can sort of imagine, because there's just one-sided, it does not have two sides. So if you try to calculate the surface integrals, you will basically run into big troubles. And because of that, the Stokes theorem doesn't apply. And typically, if you just run the program, you find a concrete example, and you can calculate the surface integrals over this, okay? And you can also calculate the contours integrals around the Mobius strip. I certainly encourage you to do that. Once you have done that, you will find their results are not the sum. So the Stokes theorem doesn't apply. But is that really the full story? Well, nowadays we have internet. In fact, if you really look into the internet, and you will find some of the useful discussion, and for instance, this is one mathematical paper. So learning shouldn't really be confined within a textbook or inside the classrooms, or just limited to professors' lectures. So you will find with exactly the same contour, there are one type of surface like this, that's the Mobius strip, okay? But there are also other type of surface sharing exactly the same cross boundaries. And if you then try to apply the surface integral through this, in fact, you will find the Stokes theorem works. So it's not just like this particular contours around the Mobius strip is sick. No. In fact, with exactly the same contours, there are two kinds of surface sharing the same boundaries. It is really due to the fact, if you really carefully look at this, you can actually play around with a rubber band. There are two ways. There are two different types of surfaces with the same Mobius strip-like boundaries. And one is this famous Mobius strip. The other one is basically like the surface inside the solenoid. If you thread through a wire of this surface on the left, you find there's zero hole, right? But then if you try to thread through a current carrying wire of this surface here, you find two holes. That is sort of thread through the surface two times and digging out two holes. And the reason why these two have different results is associated with the topological difference that I just explained to you. Okay, so let me try to switch back. Oops. Somehow it frees. Let me try to save. Oops. It's not working. Okay. I guess then somehow this whole thing stuck. So is there any other question that you would like to ask? Because my OBS somehow got stuck on the other screens. Let me get it back. I know how to save it back in real time. Okay, it is back. But then you see this so great. The screen is back. And so I do hope that you find this thinking about the Mobius strip is something really, really deep. That is to say, if now you try to really look at this whole thing here, there are two ways. One is that sort of you try to connect a surface on its side, then you get a Mobius strip. But you can also try to find a surface around this circular part, and it's almost like two circles. That is more like a cylindrical way or solenoid ways. Okay, and these two different ways will lead to two different results, and one satisfies the Stokes theorems, the other doesn't. So I guess then I would just end my videos today here. Mobius strip is sort of the naughty guys, naughty kids, revealing the subtlety of the Stokes theorem that I just showed you today. And because applied mathematics is not a very advanced mathematics course, so I didn't really go through the 4 logical steps that how we can prove Stokes theorems, let alone that why the 4 logical step breaks down for one-sided surface like Mobius strip. But for those of you who are interested in this commonly easily made and very famous logos worldwide, I think it's really time that you understand how Mobius strip dance with Stokes theorems properly. So I guess I would just then end my I guess then I would just end my YouTube live today here. Thank you for attending the lecture. Bye.